Welcome back to G Fun Facts Online. Today we are going to talk about time. Not the time you see on your smartphone or your wristwatch, and not even the time kept by the GPS satellites orbiting overhead. We are going to talk about the absolute fundamental heartbeat of the universe, and the human obsession with slicing that heartbeat into thinner and thinner slivers. For the last 50 years, we have lived in the age of the atomic clock. It is the sovereign ruler of metrology. By counting the oscillations of electrons dancing around atoms like cesium and strontium, humanity has managed to carve time so finely that if you had started one of these clocks at the very beginning of the universe, billions of years ago, it would be off by less than a single second today. That sounds perfect, doesn't it? It sounds like we have won the game of timekeeping, but for the physicists who chase the deepest truths of reality, that level of precision is simply not enough. You see, the electron, for all its utility, is a flighty thing. It lives on the outside of the atom. It is exposed to the noise of the world. To peel back the next layer of the universe's mysteries, to detect the ghostly whisper of dark matter, or the shifting sands of the fundamental constants of nature, we need a timekeeper that is harder, denser, and infinitely more stubborn. We need to go deeper. We need to go inside the nucleus. This is the story of the nuclear clock, a device that has been a holy grail for decades, and how a series of breathtaking breakthroughs in 2024 and 2025 have finally turned science fiction into reality. This is the story of Thorium-229. To understand why this is such a massive leap, we have to look at the difference between an atom and a nucleus. Imagine an atom as a vast sports stadium. In this analogy, the nucleus is a small marble sitting on the center spot of the field, while the electrons are like tiny flies buzzing around in the highest rows of the grandstands. Current atomic clocks work by using lasers to tickle those flies, prompting them to jump between seats. The speed of that jump is the tick of the clock. It is incredibly precise, but those flies are vulnerable. They are far away from the center. They are exposed to the weather of the universe. A stray magnetic field from a nearby power cable, a bit of heat, or even a collision with a stray molecule can jostle the electron, causing the clock to drift. Metrologists spend their entire careers building elaborate cages, vacuum chambers, and magnetic shields just to protect these fragile electron states. But the nucleus? The nucleus is a fortress, tightly bound by the strong nuclear force. The protons and neutrons inside that center marble are packed 100,000 times denser than the electron cloud. They are naturally shielded by the electrons surrounding them. A magnetic field that would send an electron spiraling has almost no effect on the heavy, stubborn nucleus. If you could make a clock based on the heartbeat of the nucleus, rather than the dance of the electron, it would be virtually immune to the noise of the world. It would be a clock of pure, unadulterated time. So why haven't we done it? The problem is energy. Nuclear transitions usually involve forces millions of times stronger than the forces holding electrons. To make a nucleus tick, you typically need to hit it with high-energy gamma rays, which are essentially impossible to control with the precision needed for a clock. There are no gamma ray lasers that can gently tickle a nucleus. You would need a building-sized particle accelerator. That was the status quo for decades, except for one anomaly, a quirk of nature, an isotope known as Thorium-229. Thorium-229 is the black sheep of the periodic table, but in the best possible way. Back in 1976, physicists studying uranium decay noticed something odd in the data. They realized that the daughter nucleus, Thorium-229, had an excited state that was tantalizingly close to its ground state. Usually, nuclear states are thousands or millions of electron volts apart, but this specific state in thorium seemed to be hovering just a few electron volts above the ground. This was a shocking revelation. An energy gap that small belongs in the world of chemistry, or ultraviolet light, not nuclear physics. It meant, theoretically, that this specific nucleus could be excited not by a massive accelerator, but by a tabletop laser. Physicists believe this exists because of a cosmic accident. Inside the thorium nucleus, the strong nuclear force which pulls things together, and the Coulomb force which pushes protons apart, are locked in a violent tug-of-war. In this specific isotope, those two titanic forces almost perfectly cancel each other out, leaving a tiny energy gap of around 8.3 electron volts. This is the tick of the nuclear clock. But knowing it existed and finding it were two very different things. For 40 years, the hunt for this transition was a story of frustration. It was like searching for a specific grain of sand on a beach, except the beach is radioactive and you are blindfolded. In the 1990s, researchers thought they found the energy level, built lasers to hit it, and found absolutely nothing. It turned out the initial measurements were wrong. It wasn't until 2016 that a team in Munich finally proved the isomer existed by detecting the electrons it kicked out when it decayed. Then, in 2023, a team at CERN finally managed to trap the nuclei and observe them glowing. They pinned the energy down to roughly 8.338 electron volts. The target was finally painted. The stage was set. And that brings us to the annus mirabilis of nuclear metrology, the year 2024. two heavyweights of the physics world, a group in Vienna led by Thorsten Schum and a team at Gila in Colorado led by Jun Ye, joined forces to achieve the impossible. They realized they couldn't trap individual ions in a vacuum like a normal atomic clock. It was too difficult with radioactive material. Instead, they chose a solid-state approach. They grew crystals of calcium fluoride and doped them with Thorium-229. Imagine the crystal lattice as a transparent amber holding billions of thorium nuclei frozen in place. Because calcium fluoride is transparent to ultraviolet light, they could shine a custom-built laser right through the crystal to hit the nuclei inside. In early 2024, they scanned their laser across the predicted frequency, and suddenly, the signal spiked. The thorium nuclei were absorbing the light. It was the first time in history that humans had used a laser to control a nuclear state. They then connected this system to an optical frequency comb, a ruler made of light, to measure the ticks with absolute precision. The crystal clock was born. But the story doesn't end there. While the world celebrated the crystal breakthrough, a skunkworks project at UCLA, led by Eric Hudson, was working on something even more radical, which would dominate the headlines in late 2025. They asked a simple question: why do we need a transparent crystal? The crystal method relied on seeing the photon emitted when the nucleus relaxed, but the nucleus actually prefers to decay by kicking out an electron, a process called internal conversion. So in December 2025, they unveiled the thin-film nuclear clock. Instead of growing complex crystals, they simply electroplated a microscopic layer of thorium oxide onto a stainless steel disc. It was a process likened to gold plating cheap jewelry. This material is opaque. You can't shine a laser through it. But you can shine a laser at it. When the laser hits the nuclei near the surface, they get excited. When they decay, they eject electrons, creating a tiny electric current. The team simply measured that current. This changed everything. It meant you didn't need years of crystal growth. You could make a clock chip in an afternoon. The signal was stronger, the device was simpler, and it used far less radioactive material. This marked the moment the nuclear clock went from a fragile physics experiment to a potential piece of technology. So how does this device actually work? It is a beautiful dance of light and matter. You start with a specialized laser tuned to roughly 2020 terahertz. That beam strikes the thorium sample, either the crystal or the thin film. If the laser is perfectly on time, the nuclei get excited. If the laser drifts even slightly, the excitation rate drops. A feedback loop detects this drop and instantly nudges the laser back to the peak. Then, an optical frequency comb divides those incredibly fast oscillations down into a microwave signal that digital electronics can count, outputting a precise 1-second pulse. The result is a clock that slices time into segments 100,000 times smaller than a microwave atomic clock. But why do we need this? Is it just so our GPS is accurate to the millimeter? Well, yes, but the true promise lies in new physics. The first target is the fine structure constant, often denoted as alpha. This number, roughly 1/137, dictates the strength of the electromagnetic force. It holds atoms together. The standard model says it is constant. But theories like string theory suggest it might drift slowly over billions of years or fluctuate near massive gravity fields. Because the thorium clock relies on that delicate cancellation of forces inside the nucleus, it is a monster sensor for alpha. It is calculated to be 10,000 to 100,000 times more sensitive to variations in alpha than any atomic clock. By running a nuclear clock next to an atomic clock and watching for a drift, we can test the stability of the laws of the universe. Then there is dark matter. If 85% of the universe is made of dark matter, why can't we see it? Some theories suggest it behaves like a wave. As Earth moves through the galaxy, we might pass through clumps of these waves. If we do, they could subtly shake the fundamental constants. A network of nuclear clocks would act as a planetary observatory. If a wave of dark matter passes through Earth, the nuclear clocks would glitch in a distinct pattern, speeding up or slowing down, while atomic clocks remained unaffected. It would be the first direct evidence of dark matter. And let's not forget relativistic geodesy. Einstein told us that time moves slower closer to massive objects. Your feet age slower than your head. A nuclear clock is so precise, it can detect the time dilation caused by a height difference of less than 1 centimeter. This means we can use clocks to measure the shape of the Earth. We could place a nuclear clock on the slope of a volcano. As magma chambers fill underground, the local mass density changes, altering gravity and shifting the flow of time. The clock would feel this, providing an early warning system for eruptions. Or we could monitor fault lines for earthquakes with a sensitivity impossible for seismometers. Finally, there is navigation. Deep space is a lonely place. There is no GPS. Spacecraft currently have to talk to Earth to know where they are, which takes hours. A spacecraft equipped with a rugged, solid-state nuclear clock would have its own master time. It could navigate autonomously to the Kuiper Belt or even to other stars. Of course, we aren't quite there yet. We still need to miniaturize the ultraviolet lasers, which are currently large and power-hungry. We need to manage the temperature sensitivity of the materials holding the thorium. But the impossible physics part is done. The rest is just engineering. We stand at the precipice of a second quantum revolution. Just as the atomic clock in the 1950s gave us the internet and GPS, the nuclear clock promises technologies we cannot yet fully imagine. From the 1976 hypothesis to the 2025 electronic detection chip, the journey of Thorium-229 is a testament to human persistence. We have finally cracked the nucleus, turning the most shielded, stubborn, and dense form of matter in the universe into a tool for humanity. The atomic age of timekeeping is ending. The nuclear age has begun. Thanks for listening to G Fun Facts Online.